These are Miss Mo's notes for EG.10. We're going to talk today about variation, direct, indirect, or inverse variation. So let's start with, what is a linear equation? So a linear equation describes a relationship with some dependent variable y and an independent variable x. So when we talk about a linear equation, we say, what is the relationship between x and y? Well, you take x, multiply it by some number, add some number, and that will give you out the y value. Direct variation is sort of like a linear equation. It's a type of linear equation, but in direct variation, we're just saying that y is related to x by some constant multiplied by x. So in this case, what a problem might say is, it might say y varies directly with x. Now it might not use y and x, it might use a name of a variable. So height varies directly with weight, or something similar to that. Means that as x changes, y will change as well. And how is y going to change? Well, you take x, multiply it by some number, some constant, and you'll get out y. So we should say that, what is k anyway? So let's define k. K is what we call the constant of variation. Right? It's the relationship that y and x have to each other. So you take your x value, multiply it, or divide it by some number, and that will give you out your y variable. Right? So y varies directly with x. Remember, the word varies means changes. Y changes directly as x changes. So if x increases, y will increase if k is a whole number. Right? So there's a direct relationship. So we can also say y is directly proportional to x. It's another way of saying it. So another relationship that we could have, one that's not linear, is inverse variation. An inverse variation is y equals k divided by x. So this is no longer a line, right? This relationship is that as y gets smaller, as x gets smaller, y gets bigger, right? So this is an inverse relationship. So we can say here again, y varies inversely with x. Y varies inversely with x. Or you could say y is inversely proportional to x. Right? So our final type of variation is joint variation. And joint variation simply means that my dependent variable y is going to depend on two other variables, x and z. So joint variation, so y could vary directly with both x and z. Let's do x first. So y can vary directly with x and z. So y varies directly with x and z. Or I could have y varying directly with x, but inversely with z. Right? So sometimes in your book you'll see y is jointly, y varies jointly. So you might see y varies jointly. Okay. And that's usually a direct variation, right? So jointly just means there are going to be two independent variables, x and z. All right, so maybe this seems really abstract, so let's do a couple of examples. Let's walk through the examples from the book. So I'm going to walk you through example 4 in the book. I'm walking you through this because I do want you to learn to understand how to read your textbook. So let's read this first problem. It says, the speed of a racing canoe in still water varies directly as the square root of the length of the canoe. So our very first step will be to identify the variables. So we're talking about speed here, so speed of the canoe. And we're talking about length, the length of the canoe. Right, sometimes it's nice to put your variable or your units in, and this will be measured in miles per hour. This one will be measured in feet, and we know that from later on in the problem with the miles per hour here and the feet here. All right, so that's step 1. Now let's continue to look at this very first sentence here, okay? So here it says, the speed of a racing canoe in still water varies directly as the square root of the length of the canoe. So what this helps us do is to write the equation for the model. So we know that speed is my dependent variable. It depends on the square root of the length. Now there's some constant, so it's not just take the square root of the length and that's your speed. There's some constant involved. I need to multiply the square root of my length by a number, and then I'll get out speed. So this is our model, but k should have a number here. Right? So we need to find out what k is. So let's go to part A. So part A says, if a 16-foot canoe can travel 6.2 miles per hour in still water, find the variation model that relates the speed of a canoe to its length. So really, it's giving us the information we need to find this equation, but replace k with the constant it actually is. So we know the length for part A. We know the length is 16 feet, and we know that a 16-foot boat can go a speed of 6.2 in still water, but that's what our speed was in the beginning, the speed of a racing canoe in still water. So we just plug that into this model that we found from that opening sentence. So we have 6.2 equals some constant times the square root of 16. All right, so we have 6.2 equals the square root of 16 is 4, so we have 4 times k. And now divide both sides by 4. And when you divide 6.2 by 4, I believe you get 1.55 is k. So k equals 1.55. So that's not the answer to the question. Remember, it doesn't say solve for k. It says find a variation model. So we have a model here, but it's k-less, just has k. Now we can actually write what k is. So the relationship between speed and the length of a canoe is speed times the constant speed equals the constant 1.55 times the square root of the length of the canoe, and that will give us the speed. So let's look at part B. Question B says, now find the speed of a 25-foot canoe. So for question B, put it here. So for question B, that information given to us is we want to find speed. And then they tell us length is 25 feet. So then we just plug it into the model that we just found. We don't know speed. We know k, 1.55, and we know the length. The square root of 25 is the square root of the length. So the square root of the length is 5. So we have speed equals 5 times 1.55. And thus, the speed is 7.75 miles per hour. That's how fast a 25-foot canoe will go in still water. For joint variation, let's do this example here. Kinetic energy of an object varies jointly as the weight of the object at sea level and as the square of its velocity. So, what that information gives us, that very first sentence, it tells us kinetic energy, so I'm going to use E for kinetic energy of an object. And it varies with its weight and velocity. So it says kinetic energy of an object varies jointly as the weight of the object at sea level and as the square of its velocity. So that means energy is related by some constant of variation with the weight of an object and the square of its velocity, all together in one equation. All right, so I don't want k to be in my model. So my second sentence here, during a hurricane, a half-pound stone traveling at 60 miles per hour has 81 joules of kinetic energy. So that's going to tell me what my k is, because it's given me E is 81. It tells me weight is a half a pound, and it tells me the velocity is 60 miles per hour. So plug that in. So I have 81 equals k times w, the weight, which is 1/2, times 60 squared. Right? So this one, I took it and multiplied it by 2, both sides. I multiplied this side by 2. The 1/2 times 2 becomes 1. So remember, you can multiply in any order. So I did 2 times 1/2 times k times 60 squared. So that 2 times 1/2 just becomes 1. Then I need to multiply this side then also by 2 just to keep my equation equal. So I get 162 equals k times 60 squared. So I want k by itself. 60 squared is a big number. I'm just going to leave it at 60 squared for right now. So I know k equals 162 divided by 60 squared. And then typing that in my calculator, I get k equals 0.045. So that is my constant of variation. Right? So my final model is E